In this video, we will introduce stoichiometry, including unit conversions, the idea of a mole, and look at atomic mass and molar mass. So unit conversions are going to be very important for pretty much all of general chemistry. And what you want to do when you're doing a unit conversion is look at the units that you're given in a problem, find out what units you want in your final answer, and use conversion factors to turn the units you're given into the units that you want. So a little review from math to help you with these conversion factors is that we can multiply any number by 1 and get the same number. What this means is if we have anything that's equal to 1, we're free to multiply that by anything we want. We also have the statement that if two things are equal to each other, and then we divide them by each other, that's equal to 1. So if we get any relationship, like for example, say 1 day is equal to 24 hours, we can now use this as a conversion factor. So we can multiply anything we want by 1 day divided by 24 hours, since this is just equal to 1. Or we can multiply anything we want by also the reciprocal, so 24 hours divided by 1 day. And this can be useful if we want to get rid of any of these units. When you're first practicing with these, I actually recommend writing out these equalities to begin with, so that when you're writing these fractions and using them to generate conversion factors, you make sure that you keep the right number with the right units. So this is telling me that whether I write hours on the top or the bottom, the 24 is stuck to the hours. So we can think about an example for applying this into everyday life. So here we have a quote from the famous artist Too Short and their piece Blow the Whistle. And here we can see that they have claimed to have wrapped 225,000 hours. And they're suggesting that we get a calculator and do the math. So let's go ahead and take him up on his offer and find out how many years that is equal to. And we'll do this using conversion factors. So if we wanted to do that conversion, we can start with the given unit. And we know that we want our final units to not be in hours. So we want to cancel out hours somehow. And we know that we want our answer in years at the end. So eventually we're going to need years on top. And now we need to think about ways we can get between the two. Well, we probably don't know how many hours are in a year, but we do know how many days are in a year. And we know that that's 365 days. And if we can think of a way to get from hours to days, that would help us out. And again, we do have this fact. So we know that in every 1 day, that is going to be equal to 24 hours. And now we've set up a conversion problem that we can do. Now, when you plug these in on your calculator, depending on the calculator that you're doing, there's a few things that you want to be careful with. So when you plug these in, if you don't include all the parentheses, your calculator likes to mess up when it does division and multiplication. So if you're just using your phone for calculations, my recommendation is to multiply everything across the top and write that down. So in this case, that would be 225. 0, 0, and we'd see the days would cancel out and the hours would cancel out, so it would just be left with years. And then multiply everything on the bottom and write that down, and in this case that's equal to 8760. And then just do one division on your calculator so that it doesn't mess up the order of operations. And when we do this, we can see that Too Short was wrapping for something like 25.7 years. Next, we'll talk about atomic masses, the mole, and molar mass. Okay, so for an atomic mass, let's consider this species. So here we have carbon, and this is specifically a carbon with a mass number of 12. So that would be 6 protons and 6 neutrons. And we actually defined the mass of carbon-12 as exactly 12 AMUs. So AMU is a unit of mass. And 1 AMU is equal to 1.66 times 10 to the negative 24th grams. So if we were to calculate the mass of 1 carbon in grams, that's 12 of these AMUs, so that would be 12 times 1.66 times 10 to the negative 24th grams. And that would be equal to 1.99 times 10 to the negative 23rd grams. So is this something that we could actually weigh? Could we go out and weigh 1.99 times 10 to the negative 23rd grams? And just as a reminder about scientific notation, this is the same as moving this decimal place 23 spots, which is still something like 100 times less than a billionth of a billionth of a millionth of 1 gram. So no, not really something that we can measure. But since in chemistry we do want to work with individual atoms, we need to come up with some system that represents a huge number of atoms, and this is where the idea of a mole comes in. The mole is just another version of counting, and you'll notice these are all set up as equalities. So these are all things that we could use as a conversion factor. 1 pair is equal to 2 of something. 1 dozen is equal to 12 of something. We could say 1 billion is equal to 1 times 10 to the 9th of something. And 1 mole is just another number. This is equal to 6.022 times 10 to the 23rd of that thing. Sometimes, rather than writing this number, we'll just use a shorthand and write n, or n sub a. And this stands for Avogadro's number, who is one of the people who first formalized this value. Okay, so how big is a mole? Well, it kind of depends on what we're counting. So 1 mole of something is always 6.022 times 10 to the 23rd of that thing. 1 mole of water molecules is about 18 milliliters of water. So that's something that's fairly reasonable. It's like a fraction of a shot. 1 mole of pennies, however, that's enough pennies to cover the whole entire world about a quarter mile deep. So a mole is not a lot if we're talking about individual molecules, things that are too tiny for us to normally weigh, but we usually wouldn't talk about a mole of something that's macroscopic. So now we can talk about the mass of things in terms of molar mass. So rather than thinking about the mass of one individual atom, we can talk about the mass of a mole of atoms. So remember, 1 mole is 6.022 times 10 to the 23rd. 1 carbon atom weighs 1.9 times 10 to the negative 23rd grams. So we can find out the mass of 1 mole of carbon-12 atoms by using this calculation. So if we had 1 mole of carbon atoms, we can find out how many individual atoms that is, since we know how much an individual atom weighs. And to do this, we'll use this as a conversion factor. So 1 mole is equal to 6.022 times 10 to the 23rd. And then we know that each carbon atom is the same thing as 1.99 times 10 to the negative 23rd grams of carbon. And so the number of atoms will go away, the moles will go away, and we'll see that 1 mole of carbon atoms is the same as 12.0 grams of carbon. And remember, this is 12.0 grams of carbon per mole of carbon, or we could say 12.0 grams per mole. And because we have grams per mole, this value is called the molar mass. So 12.0 is the molar mass of carbon-12. If we look on the periodic table, we can see those often give the atomic numbers, the atomic symbol, and down here we also often see a mass value. Now this is the average atomic mass in AMUs or in molar mass. And you'll recall from this slide that 1 carbon-12 is exactly 12 AMUs, and we found that 1 carbon-12 is exactly 12.0 grams per mole. And so you may notice there's an analogy here. The value for AMU is such that 1 AMU is actually the equivalent as the value in grams per mole. So we can interconvert AMUs and grams per mole fairly readily. So when we see this average atomic mass in AMUs, that would mean an average carbon is 12.1 or 12.01 AMUs, or an average mole of carbon is 12.01 grams. So there's something a little weird here. If we defined the AMU as being exactly the mass of a carbon-12, why is the molar mass of carbon not exactly equal to 12 for all carbon? And that's because there are different isotopes of carbon. So not every carbon is a carbon-12. If we look at all the isotopes of carbon, we can see that for carbon-12, it is indeed exactly 12.00 grams per mole, and this does make up about 98.89% of all carbon. Carbon-13, on the other hand, is a little more than 13 grams per mole. This is because neutrons and protons don't weigh exactly the same, just very similar. And we can see this makes up about 1% of all carbon. And then we also have carbon-14, which is detectable, but it's very trace amounts, so not within this amount of sig figs, and it has a mass of 14.0032 grams per mole. And so what we can do is calculate the weighted average mass of carbon. And to do this, we can take the abundance, convert it into a ratio, and take the mass of each species. So for the weighted average, we'd have the mass of carbon-12, 12.000, and convert the abundance from a percent to a decimal, so 0.9889. And then we'll do that for every species and convert that to a decimal. And since this is negligible, that would just end up being 0. And so if we add these two together, we get a value of 12.01 grams, which is what we see on the periodic table. So the value we get there for the molar mass represents the fact that if we were just to take out a random sample and use that in our experiment, it would be a mixture of the isotopes. And so to get a mole of that carbon mixture, we'd expect on average for it to weigh 12.01 grams. And most elements will have multiple isotopes, so you'll see this as the case for most things on the periodic table. We should also be able to practice working this problem backwards. So if we wanted to find the abundance of one particular isotope given some information, we can look at this type of problem. So say we have silver, and we know that it has two stable isotopes, and we know the mass of those two isotopes. And let's say we also know the average molar mass from the periodic table. This question is asking us, what is the abundance of silver 107? Okay, so this will be typical of some of the trickier problems that we'll see. And in this case, the best thing to do is to sort of take all of the information that we have and figure out where we can go from there. So in this case, remember to find the average molar mass. This is going to be the weighted average of all the species, so this will be the abundance times the mass for every species. And in this case, we know the mass of both, and we know the average mass. So from this step, it looks like we have one equation and two unknowns. And the question is asking us to find this one unknown, the abundance of 107. And do we have enough information to solve this? Well, normally if we said we have one equation and two unknowns, you might recall from algebra that the answer would be no. But there is one other thing that we actually have here, and that has to do with the total abundance. So if these are the only two isotopes, we also know that if we add the abundance of both together, that has to equal 100%. Or if we're writing it together as a decimal, they have to add up to 1. So we actually have two equations and two unknowns. So this is just enough information to solve this problem. So let's go ahead and write down all of our values and work this one out. So if we have our average molar mass is 107.868 AMUs, and we know that's equal to the abundance of silver 107 times its mass, plus the abundance of silver 109 times its mass. And then our second equation, that 1 is equal to the abundance of 107 plus the abundance of 109. And from here, there's actually two different ways to solve this problem. So solving a system with two equations and two unknowns. One of these is posted up on Gaucho space, so the method of substitution. So if you want to see that way and use that method, that would work fine, so you can go ahead and do that. For this presentation, I'll show you another method where we can add and subtract two different equations. So in order to get one of these, and we know that we want the final answer in the abundance of 107, what I can do is multiply this whole equation through by something that'll help me cancel out this value right here. So what I'm going to do is multiply this whole equation by negative 108.910. And so what we get after that step is 1 times negative 108.910 is equal to negative 108.910 A107 minus 108.910 A109. And now what I can do is just add these two equations directly. And I get negative 1.042 is equal to, these ones will cancel out, that's how we designed it, negative 2.003 A107. And then dividing both sides by negative 2.003, we get that A107 is equal to 0.52. And if we wanted to convert that to a percent, that would be 52% silver 107. And again, if you want to see the other method for solving these two systems, this is also written out on our course webpage. The next thing we'll look at is calculating the molar mass of molecules. And this is fairly straightforward. We just add together the mass of each atom in that molecule. So for example, if we wanted to find the molar mass of methane, we'd look up the mass of the elements on the periodic table. So carbon is 12.01, and we have one of them. If we look up the hydrogen, we have 1.0079, and there's 4 of them. So adding these all together, we'd get that CH4 has a mass of 16.0416 grams per mole. And note, whenever we're finding the molar mass, unless it's otherwise specified, we're assuming it's the natural mixture of isotopes. So we just take the values straight from the periodic table. And so for one last little bit of practice, take a look at this and see if you can calculate the mass of barium phosphate. And in this case, this is the correct answer. Let's see how we would get that. For barium phosphate, we'd have to recognize that barium and a polyatomic ion, so we have an ionic compound. Barium is in group 2A, so this is barium 2+, with a 3- charge on phosphate. That means our formula would have to be Ba3 PO4 2. And so this means we have 3 bariums, so that's 3 times 137.3, plus 2 phosphates. So we have to remember the 2 outside the parentheses, so that's 2 times 31.0. And 2 times 4 is 8 oxygens, so 8 times 16.0. And you plug all those in, and you should get 601.9 grams per mole.